This is part 3 of the vector spaces chapter, and we continue with the introductory definitions. Now we start working with matrices. We already worked with matrices because we consider them as vector spaces when we consider scalar multiplication of matrix and addition of matrices. Now we turn to matrix multiplication. If A is a P by Q matrix and B is a Q by R matrix, so that means that these second part of the dimension of A and the first dimension of B match, then the product A times B is a PR matrix where P comes from the first dimension of A and R comes from the second dimension of B. And this can be denoted, this AB product matrix, as a C matrix with entries, KL entry, which is the sum of AKJ BJL, and adding this up as J goes from 1 to Q, and K goes from 1 to P, and L goes from 1 to R. So K is the row index, and we keep the row index of A here, and L is the column index of the product matrix, and that's coming from the column index of the B matrix, and we sum with respect to these J indices, which is the column index of A and the row index of B. There are alternative forms to write this product matrix or to calculate this in a formal way. We can consider CKL as the product of the kth row of A and the lth column of B. So if AK is the kth row and BL is the lth column, then this is a 1 by Q matrix, which is a row vector, and this is a Q by 1 matrix, which is a column vector. And then because we have here Q columns and Q rows, that means this multiplication is defined again, and this is exactly this summation that we get from here. For example, if we consider this A matrix, this is a 2 by 3 matrix, 2 rows and 3 columns, and B as this matrix, which is a 3 row and 4 column, so 3 by 4 matrix. 2 by 3, 3 by 4, 3's match. That means AB is defined, and AB, A times B, will be a 2 by 4 matrix. 2 is from here and 4 is from there. And we calculate the following way. The 1, 1 entry, first row, first column, minus 3 times minus 8, plus 9 times 2, minus 2 times minus 1. Then the first row, second column gives us the 1, 2 entry. So minus 3 times minus 6, 9 times minus 3, and minus 2 times minus 2. And so on. For example, from the second row and the third column, we get the 2, 3 entry, which is this one, the second row, third column, comes from the second row, third column. So 6 by 6, then 1 times minus 5, and 2 by minus 6. And then after we write this out, then we do the multiplication and addition, and then we get the product matrix, which is a 2 by 4 matrix. So in a special case, when in this AB product, B has the size Q times 1, so R is 1. Q times 1, that means B is really a column vector, which means a vector in the FQ vector space. Then what we get is that AX matrix vector multiplication, and the result is P times 1, which is another P vector. For example, if we consider this A matrix, which is a 2 by 3, an x vector, which is a 3 vector, which means it's really a 3 by 1 matrix, then A times x will be first row, first column, that's the 1, 1 entry, minus 15, 0, 14. And then 2, 1 entry, 30, 4, 63, add it together, we get minus 197 for the new resulting vector. Special matrix identity matrix, I sub n is a n by n matrix. So if we denote by A this matrix actually and the Aij entry, this is the so-called Kronecker delta, which means delta ij is 1 if I equals to j and 0 if I is not j. And this In matrix is called the identity matrix. When I equals to j, that means the row index and the column index are the same. These are actually called the diagonal elements. So for n equals to 3, we have a 3 by 3 matrix where only these entries are 1 and all the rest of the entries are 0. This In matrix has the property that if B is a P by N matrix and C is an N by Q matrix, then we can do the B times In multiplication because N matches the size of the N, and B times the identity matrix is B, and similarly I times the identity matrix times the C matrix is just the C matrix if the dimensions match and if these multiplications are defined. So this has nothing to do with the vector space properties. If you check the vector space properties, we don't have anything like this. Also note that matrix multiplication is not commutative. That's very important. Of course, if A is a P by Q matrix and B is a Q by R matrix, then in this case A times B is defined because Q matches in the 2 dimensions. But B times A, the other order multiplication, is not even defined unless R matches P. P equals R. And even then, AB has size P times R, and BA will have size Q times Q. So it's questionable whether these will be at all the same dimensions. But even if they are the same dimension, because it could be that A and B are both n by n matrices, and that means that AB is an n by n matrix and BA is an n by n matrix, still it is not true in general that AB equals BA. On the other hand, we have some other properties, not commutative, but some other nice properties of matrix multiplication. We have the associative property, which says that if we have 3 matrices A, B, C, then if we can do the multiplication because the sizes match, if the multiplications are defined, then AB times C is the same as A times BC. So we can regroup the multiplication. Note that the multiplication is binary operation, so if you have 3 matrices, then we have to do it in pairs. But since it doesn't matter how we group it, then we might as well just write A times B times C. Also, the matrix multiplication is distributive with respect to matrix addition. So if you have 3 matrices, or actually 4 matrices, or whatever number, the point is that the question is whether or not these operations are defined. So we have to make sure that the sizes match. Then A plus B times C is the same as A times C plus B times C. So this is like multiplying from the right, the sum. And if we multiply a sum from the left with appropriate size matrices, then we get also that A times C plus D is A times C plus A times D. So we can distribute the multiplication through the parentheses. If A is a size n by n, then A is called a square matrix. And then for k positive integer, we can define the kth power of A to be A to the k as the product of A k times by itself. Note that this is not entry by entry power. It's kind of easy to check that that's not the case. So if you have to calculate, for example, 2 by 2 matrices third power, that means you have to multiply together the matrix by itself 3 times. And of course, then somehow you have to group this. You have to do it in pairs. If we do the first one, we get a matrix, and then we multiply it with the A matrix again, and then we get some new matrix, which is A cube. And it's easy to check that this is not entry by entry power. It has nothing to do with entry by entry powers. If we have 2 matrices, for example, A is a P by Q matrix and B is a Q by N matrix, then these matrices can be considered as row vectors of column vectors or column vectors of row vectors. So if we have the A matrix, we can take the columns and put next to each other, and that's the matrix. First column, second column, third column, and so on. So this is a row vector of column vectors. But we might as well also look at this as first row, second row, third row, and so on, the pth row. So this is now a column vector of row vectors. It's just a different notation. And we can do the same thing with the B matrix. The number of columns is different, so this is now n row matrix of n column matrix, or column vector of q row vectors. And then if we want to write A times B, the original definition was, well, that's not the original, but the alternative definition was to do this row by column, the multiplication. So that will be the first row with the first column, and the second row with the second column, and so on. So that means it's like a column vector multiplied with the row vector. And note that this is a p row and 1 column multiplied by 1 row and n column. So the result is p by n, and it's supposed to be p by n matrix, the product matrix. But another way to look at this is that AB, when we collect it into a column vector and we multiply this with B, then we can multiply row by row this column vector with B. And we get the first row of A times the B matrix, and so on, the pth row of A times the B matrix. If you check the sizes, everything matches. So the first row has Q entries in it, and that means that we can multiply that row with the B matrix because that has Q rows. We can also look at this as A times B being A multiplying the row vector of the columns of B, and then multiply through with A, entry by entry, to get the result. Or multiply the row vector of the column vectors of A with the column vector of the row vectors of B. So this is a 1 by Q, and this is a Q by 1 matrix, seemingly. But when we multiply the A column with the A's column with the B's row, actually the column itself has p entries in it, and the row of B has n. So this way we get p by n matrix. And in fact, then the way we do this row vector and the column vector multiplication is that we multiply the ith entry with the ith entry in the second vector, and we add this up. But again, these are again vector multiplications, and the result of this is actually a p by n matrix. Yeah, it's kind of tedious to look at this, but in some theoretical parts, actually it can be useful to change the notation and do it in different ways. So this is actually special cases of so-called block multiplication. It's often more convenient to split up large matrices into blocks. So these are submatrices, or these are called blocks of number. And they don't have to be square parts, they can be rectangulars, but again, we have to make sure that the sizes match. And then instead of multiplying a large matrix like A with another large matrix B, A times B can be written as multiplication of these blocks, like AI1 times B1J and AI2 times B2J, as I goes from 1 to 2 and J goes from 1 to 3. And if some of the parts here have special properties, then it might be more convenient to do it this way than to do the whole large A matrix with the large B matrix. The sizes have to match, to make sure if you have to do this kind of thing that everything matches. Next, the transpose of a matrix. So if you have a P by Q matrix A, then its transpose is a Q by P, so the dimensions interchange. From P by Q we get Q by P. And the property of this is that the kth row of this is equal to the kth column of the original matrix. It's just the column is laid sideways. So you can also say that the ij entry of A equals to the ji entry of its transpose. And we use this A superscript T for the transpose notation. For example, if you have a matrix which is 2 by 3 matrix, then the transpose will be a 3 by 2 matrix, and the first row becomes the first column, the second row becomes the second column. It's easy to see that the transpose of a transpose gives you back the original matrix. It's some short exercise to see that the transpose of a product is not just transposing factor by factor, but we have to change the order. So AB transpose will be B transpose, A transpose. The order of AB have to be switched. There's also called a special Hermitian transpose of a matrix. So here, in addition to transposing the matrix, we also take the complex conjugate of the original matrix. So clearly, if the matrix is not complex, it doesn't have complex entries, then that conjugation doesn't do anything. But if the matrix has complex numbers in it, then remember that the complex conjugation means that you switch the sign of the imaginary part. So the Hermitian transpose, denoted by A superscript H, is that we transpose it. So the first row becomes the first column, second row the second column, but also conjugate, take the complex conjugate of the entries. So 1 minus 2i becomes 1 plus 2i, 3i becomes minus 3i, 5 is a real number, so it doesn't change. Then 6 minus 4i becomes 6 plus 4i, 0 is a real number, it doesn't change. And 1 plus 7i becomes 1 minus 7i. As for the transpose, we can also see that the Hermitian transpose of a Hermitian transpose gives you back the original matrix, That's because the transpose does it twice, and also the complex conjugation gives you back the original number. When you complex conjugate twice a complex number. And similarly, the transpose, the Hermitian transpose also has this property that when you take the Hermitian transpose of a product, A times B, when you want to do it factor by factor, you have to change the order of the multiplication. So you get B A Hermitian transpose times A Hermitian transpose. Next, the zero matrix. So a big zero or a big O is used for the zero matrix, and the subscript P by Q, P times Q, denotes the size, that this is a P by Q matrix, and all of its entries are zero. And sometimes we omit the subscript if it's clear what the size is. So usually we use it for addition or multiplication, and clearly the only way this is defined if this matches the size of the A. And the zero matrix plays the role of the zero vector in the vector space of the P by Q matrices. So that means that if we add the zero matrix to A in any order, A plus 0 or 0 plus A, that just leaves the A matrix there. Next, the inverse is, if A is a P by Q matrix, so F means that it's either real or complex, doesn't matter, everything holds the same way. Matrix C is said to be left inverse of A if C times A equals the identity matrix. And of course, if we multiply C with A from the left, or A with C from the left, that means that to get the identity matrix, the second dimension of C must match the first dimension of A. And to get the identity matrix, we need that at the end we get a square matrix, Q by Q matrix. So that means the first dimension of C must be Q. If there is a left inverse for A, then A is called left invertible. And similarly, we can have right inverse for a matrix A. That would be the matrix B, which has the size Q by P, so that when you multiply A from the right, that's why it's called right inverse of A, that you multiply A from the right with B, you get the identity matrix of size P. Again, the dimensions have to match. And it, as you see, it turns out not to be the same as before, because A doesn't even have to be a square matrix. It can be a general P by Q matrix. And again, if the right inverse exists for A, then A is called right invertible. If matrix A has both left inverse C and right inverse B, then it turns out that B must be equal to C. And to see that, and notice that the size is supposed to match anyway, but the way we can prove this, that the left inverse and the right inverse are the same if both exist, we can write C as C times I, where I has size P by P. So we have this property that the identity matrix doesn't change matrix when we multiply with it. But then we can write this identity matrix as A times B, because according to the assumption, it has A has a right inverse B. And then we have that the matrix multiplication is associative, so we can regroup this to write as C times A. Then we get that C is the left inverse of A, so C times A is the identity matrix of size Q by Q. But then when you multiply this with B, we get that this is B. So we get that C equals B. With this, actually, we also showed that if A has both left and right inverse, then it has exactly one left inverse and exactly one right inverse, and the two are equal. Because this says that the left inverse must be equal to the right, and if you have another left inverse, that must be also equal to that same right inverse. So if both the left and right inverse exist, then we say that A is invertible. And then we say that it has an inverse, and this inverse is denoted by A minus 1. So this is like the power, negative power, but it has a completely different interpretation when you try to calculate the inverse. So it's the same notation as for the reciprocal of a scalar, but it's not reciprocal. Then we also have for the inverse that if A and B are both invertible matrices of the same size, then the product A times B is also invertible. And the inverse of the product is the product of the inverses, but again you have to change the order, like for the transpose, also for the inverse, AB inverse is B inverse A inverse. And to show this, we can write that AB times B inverse A inverse, the product is associative, so we can regroup this and write A times B inverse, but this is the identity matrix, and that means that when you multiply, for example, A times I, that leaves us with just A, and then A times A inverse is I. So this means that B inverse A inverse is the inverse of AB, and we already know that the inverse is unique, so that means that B inverse A inverse must be AB inverse. So let's look at this example. This following matrix has no left inverse and no right inverse. The matrix is 2, 2, 1, 1. And if you want to show this, note that we haven't talked about determinants so far. In undergraduate linear algebra course, you might have learned that how to use determinant to figure out whether or not a matrix has inverse. But in this course so far, we don't have this, so you're not supposed to use something that you haven't seen in this course. All we know is that if A has a right inverse, then that means there is a matrix B such that A times B is the identity matrix. If you write this out, what it means with the notation B11, B12, B21, B22, then the 1, 1 entry of the AB product is 1, and if you write it out, how you get this is the first row times the first column, first row of A times the first column of B. So this is 2B1, 2B11 plus 2B21. We can also factor out 2 from here to get 2 times B11 plus B21. And the 2, 1 entry, for example, of this AB product is then the second row times the first column, and that's supposed to be 0. The second row is 1 times B11 plus 1 times B21, so we get 0. But if you compare these two equations, we get that 1 equals to 2 B11 plus B21, but B11 plus B21 is 0, which is 2 times 0, 0, which is contradiction. That means A cannot have right inverse. Very similarly, if you assume that A has a left inverse, C, denoted by C11, C12, C21, C22. So if you multiply out C times A, then the 1, 1 entry, which is supposed to be 1, is 2 C11 plus 1 C12. And then the 1, 2 entry, first row times second column, supposed to be 0, but it's the same 2 C11, C21, C2, C12, which again gives the contradiction that 1 equals to 0. So that means that A cannot have a right inverse either. Then we can see that the matrix A, which is 1, 0, 1, 0, 1, 1, it's a 2 by 3 matrix, has at least 2 right inverses but has no left inverse. It's very similar as we did before. If there was a left inverse C, that must be of the size 3 by 2, and then CA equals to the identity matrix of size 3 by 3. Then what we would get with the multiplication is that the 1, 1 entry is just C1, and that's supposed to be 1. The 1, 2 entry is only C12 is picked up, that's supposed to be 0, and then the 1,3 entry is C11 plus C12. And then from here what we get is a contradiction. Again, that means you cannot have a left inverse. But if you look at the right inverse, writing out some arbitrary B matrix of size 3 by 2, so that when you multiply with A with B, you get a 2 by 2 matrix. It's supposed to be the identity matrix. If you write out this multiplication and compare the entries, we get some set of equations, and if you try to solve this, you don't get a contradiction. What you get is something like that B21 is B11 minus 1, B12 is B22 minus 1, B32 is minus B12, B31 is minus B21, and then it looks like that B11 and B22 are arbitrary. So for example, if you choose 1, 1 for B11 and B22, you get all the other entries are 0, so then B has this form. And if you check, A times B is really the identity matrix. And then if you choose some other number for B11 and B22, for example 3 and 4, then you get some other numbers and some non-zero numbers for the rest of the entries. But it turns out that if you multiply it out, A times B, again you get the identity matrix. In fact, it turns out that in this case, since B1 and B2 are arbitrary, we have infinitely many choices. And this is true in general, that for a given matrix, this matrix has either 0, 1, or infinitely many right inverses and the same number of left inverses. Let me also mention that inverses are almost never used for solving a linear system. If A is a given matrix that has an inverse, and B is a given column vector, then you can write this matrix vector equation down, Ax equals B, and this represents a linear system with unknown vector x that has components x1, xn. Also note that one useful notation with the transformation is that if you write a column vector, that takes up a lot of space, especially if you write it in a text. But while x is supposed to be a column vector, if you write it as a transpose of the row vector, it's just one row. You can write this in one row, and it's kind of nicer for typesetting. So anyway, if you write down Ax equals A and then Ax equals B as an equation, and you multiply this with the inverse of A from the left, both sides, that's also important that we multiply from the left, then we get A inverse Ax equals A inverse B. A inverse A is just the identity that just leaves X on the left, and then on the right we just have A inverse B. So that gives a solution for the unknown column vector X. But this is almost never used, because what this process would require is first calculate the inverse and then multiply it out. And first of all, this is more work than just using the Gauss-Jordan elimination, which is important. If you do huge number of calculations, then you don't want to do more work. And it has other problem actually. The other problem is that calculating the A inverse and then multiplying it with the B introduces more numerical error, which is also a problem. Of course, all these tedious calculations are very simple, and they are perfectly fine for computers to do. Especially if the matrices are large, you don't want to do it by hand. So MATLAB software is the de facto software which is used for engineering and applied mathematics. MATLAB stands for Matrix Laboratory, and next I will do some demonstration of how to use it.